You want to see how we do 3D animation in computer science, or you want to be able to read this formula? Hi, I'm Jerome, and today we'll be looking at animation data. First thing first, when we want to animate, we will usually start from a skeleton, and a skeleton is a hierarchy of transform, meaning that if I move one of my bone, I will have all its children move with it. In computer science, when we have a hierarchy, usually we represent this as a tree. And so I have here the tree that represents my skeleton with the hips, spine, arms, and so on. I can give an index at each of those transforms, and I will go depth first. So we'll go from 0 to 7 in the order of my tree now. And because I have all those index, I can easily find the parent of each transform. Now, to speed things up, usually what we do is that we transform that tree into an array, and I will have an array of transform, and in my case here would be an array of matrix 4, so I can encode translation, rotation, and scale directly in each of those matrices. And then we also have the list of the parents that we computed before. So we have a list of all the transform and list of all the parents. We have all the information that was important for the skeleton itself. If we want to make a pose, we need to parameterize the pose with the minimum needed informations. And in this case, if I give the position of my root and the rotation of every bones, I can pose my character in every pose anywhere in the world. So P0 means the position of the first bone, and all the Qs represent the rotation. Q because we will be more likely using quaternions. If I want to do a motion out of this, a motion is a function of time that is parameterized with the same information, but each parameters now need to be also a function of time. So now I have a motion that can change through time, and that's usually the formula we'll see in all the papers. Because I will be using the Ubisoft LaForge animation database, so the LaFan one, they encode the data and the motion a bit differently. And so what they do is that they decide that a motion is parameterized by two tensors, one for the position and one for the quaternions. And each of those tensors are basically all the positions through times for every bones and all the quaternions through time for every bones. If we look into the tensor for the positions, for instance, what we see is that is a Numpy array that has a discrete time that has 30 frames per second. And so you'll have a bunch of rows, one row per frame. And then for each of those rows, you will have a column for all the bones. So you will get one frame with all the bones, all the positions for every bones. And now because all those positions are actually 3D vectors, basically all the positions will be X, Y, Z, and then you get a 3D vector that has number of frame, number of bones, X, Y, Z for the position. And that would be the same for the quaternion. So in our case, the tensor for the position is frame count, bone count 3, and the tensor for the quaternion is frame count, bone count 4, because you get the W coming from the quaternion also. So let's see how we can import this inside of Numpy. What I have is a framework that is built on top of IPy widget that allows me to directly draw a 3D inside of my Numpy. And I will load my character and I will display this character so you could see what we have here. So the structure of the skeleton, as I said, you get the root. Well, I get the root here on the ground and I get all my root, all my transform. So they each time I transform and you get the link between them. So that's my skeleton for my character. And if I load one animation, for instance, you could see how the framework gives us this these tensors. So for the positions, I get 7,000 frames, 22 bones, and XYZ, and quaternions, 7,000 frames, 22 bones, and XYZW for the quaternion. And if I want to render this animation, I can see this animation. The particularity of the Lafan is that they've given the transform for every bone inside of the animation directly. So you could see that my character now is a bit deformed compared to what the Lafan animation has. And that's because I've applied the transform coming from the animation onto my skeleton. So I've basically changed the shape of my skeleton. What I will want to do is to make sure that I will match the bone translate from my skeleton. And for this, I will reload the animation, but giving it the character I want to use in my case. And now I will actually have the same animation, except that is mapped onto my character. So the rotation comes from the tensors, and I've replaced most of the translate with the translate of my skeleton except for the root. You could see that my character doesn't have the same shape, doesn't have the same size. So what happened is that I have my feet on the ground in this case, but that's not to worry. And one other thing that we have is that my skeleton has a root on top of the hips, except that the Lafan one starts from the hips directly. So my animation has start from the hips, and you see that my root stays there in 0, 0, 0. When we are in video game, usually what we do is to use that root to represent where the character would be inside of the world. So we don't start the animation at the hips itself. Usually we have a root on the ground, and the root represents the entity itself, represent the capsule for the physics where you collide and that kind of stuff. So we tend to have a root that stays under the character as close as possible. So what I would do is that I would start from the animation here, from the Lafan, and I will compute automatically a root that goes under the hips of my character. The way I'm doing this, it's basically taking the position of the hips and I project it on the ground, and I take the forward axis of the hips that I have here. So get my forward axis here, and I will also project the rotation on the ground. So I project the axis, I compute the angle around. So I don't have something that rotates in any direction on the ground. I'll only rotate to have the forward axis of the character basically on the ground, and I get the projection. And so I project the hips, and then because I will be moving the root, it will actually also move the hips. So I need to compute the inverse matrix to bring this back at the same spot. And that's what is computed here. So projecting on the ground and bringing back the hips under the root. And what you have then is this. So now we have the same animation as before, except that you could see my root is right under my hips, rotate with my hips. So it gives me an indication of where the forward is and that kind of stuff. And the advantage of having a root like this is basically now I could decide if I want to play the animation on that root or not. And I can say, stay here in 0, 0, 0. And that's allow you to have the animation on spot. If you actually want to have the animation on spot for some reason, you could also say that you want to turn off the rotation and you have it completely on spot as a local motion relative to a root motion that now is completely turned on and off. So you could turn on and off just the root, keeping a bunch of the motion and that kind of stuff. That's the advantage of having a root at the bottom. What you could see, as I said before, is that my character doesn't have the same proportion as the character from the Lafan one. So I have my foot that are on the ground, and also they are sliding. If I bring back my character, where are you? The feet position will not be static on the ground. They start to slide a bit and all that kind of stuff. And that would lead us to the study of our first paper in the next video. So I hope you enjoyed this one. And if you want, you could subscribe so you could know when I will start to publish the next videos studying those papers. See you next time.